Hello, everybody. Welcome to the continuation of the functions of the heart. We are going to be looking at the electrical activity in the heart through what's called an electrocardiogram or EKG. And we'll also look at the consequences of an EKG on cardiac muscle. We're going to be seeing what's called the cardiac cycle, what's happening in terms of the chambers of the heart with respect to three things. We're going to be looking at the volume of these chambers and consequentially the pressure changes, and of course we're also going to be looking to correlate all this with the sounds of the valves closing. So we're going to be looking at all of this in detail in this lecture. So if you look at an EKG, this is again something that we're going to be doing in lab. You're going to be doing your own EKGs and your partners, and you can see that the EKG has a couple of important waveforms, and the x-axis of this is the most important. The y-axis is not important. So the millivolts is not important at all. So don't worry about it. This can vary significantly from person to person, but the time, which is on the x-axis, that is really what's important. So the time intervals is really what that counts. So if you look at the waveforms, we have what's called a P wave, and notice in terms of intensity, it's really small. Makes sense because P wave correlates with atrial contraction. I've told you already that the atrial cardiac muscle is really thin, and again we'll see why that's important when we do blood pressure. The atrial walls can sense the volume of blood, and if you want it to be a sensor for blood volume and blood pressure, it has to be thin. If it's too thick, then it becomes insensitive, right? So it's thin, and so we take advantage of that. And the atrial walls being fairly thin, they don't need a strong signal. So as you can see, the P wave is quite short. It's not very intense. And then it's followed by a very intense wave complex called the QRS complex. Here's Q, here's R, here's S, right? So we have the QRS complex, which correlates with two events: one, ventricular contraction, and atrial relaxation. So the atrial relaxation gets masked by ventricular contraction. Ventricular contraction is so strong. Again, understand that these are voltage changes, so we're measuring electrical activity. And then we have the T wave, which is somewhat broad and a little larger than P, but definitely smaller than QRS, right? And T corresponds to ventricular relaxation. As you can understand, you want that to be a fairly slow process, right? So these are the different waves of the EKG. That's really very important, and you have to understand how this correlates with contraction. So the important idea is P waves help contract atria, QRS helps contract ventricles, and T wave helps relax the ventricles. Okay, so these are important ideas because contraction always causes pressure to go up, volume to go down, and relaxation always causes volume to go up, pressure to go down. So you're creating suction. So it's a very important theme here. Pretty common sense, but you have to make sure you remember that at every step. So what I have shown here is the cardiac cycle, and I'm going to walk you through this fairly slowly, and I have two different representations because again this is a complicated set of events, and you do need to know this really well. Okay, so a couple of things you have to pay attention to. So in this graph, you have to pay attention to the pressure changes. You also have to pay attention with respect to time and how that correlates with a normal EKG, right? And there are two sort of blue shaded areas that demarcate isovolumetric stages. And isovolumetric means constant volume. Volume is not changing. So before I jump into this, by this time you would have done the heart anatomy lab. So I'm sure you understand that the atria and the ventricles, the flow of blood is controlled by the tricuspid and the bicuspid valve, respectively. Remember, these are mechanically gated valves, meaning you put pressure on them, they open, but they only open in one direction. So they only allow unidirectional flow. The same thing happens with the semilunar valves that are found both in the pulmonary artery as well as in the aorta. And understand that the semilunar valves are also mechanically gated, and they always open to the side where pressure is low. This is just like opening a door, right? You push on the handle of the door, it's going to open to the side where there's no force, right? So that is opening in response to a force gradient or a pressure gradient, right? Pressure is nothing but force per unit area. Okay, so there's a lot of detail on this graph that I'm not going to really test you on, like A wave and the C wave and the V wave and the Y descent and the X descent. I'm not going into all that, but there are some events that you will need to know, but I don't really need you to know those names. Okay, so please don't worry about that. But these refer to right atrial pressure. Okay, and so again, here's your EKG. You're pretty clear about EKG. We just went over that, right? So the key thing to understand is, as cardiac muscle is contracting, whether it's the atrium or the ventricle, it doesn't matter. As the cardiac muscle is contracting, the chamber is going to increase in pressure. Now, also understand that the atrium is very, very thin, and the ventricle is very, very thick, right? So it takes a lot less effort to produce a very small amount of pressure increase in the atrium. But in the ventricles, it takes a lot of effort, but that produces a pretty big magnitude change, and it happens very slowly, right? Because it's a very thick muscle group, correct? So keep all this in mind. Also, valves open when you meet a certain threshold pressure. When you put enough force on the valve will open to the side where the pressure is less, right? So keep this in mind. We are looking at cardiac cycle, and cardiac cycle is typically studied primarily in the left side of the heart. Not that it doesn't exist in the right side. The same process happens on the right side. But here's a really important fact. The left side of the heart undergoes a lot more pressure changes, so it's a lot easier to measure compared to the right side of the heart because the right side is pumping blood to the lungs, right? And the lungs are right there. What do you need high pressure for? Also, if you increase the pressure of the right side, blood is being pumped with high pressure to the lungs. That's going to damage all the fragile lung capillaries, right? And it's going to cause severe damage in the lungs. So we cannot afford that, right? So purposely, the right side, the right ventricle is a lot thinner. It generates a lot less force. Most likely, the fibers going to the right ventricle are going to be less in number. So you are pushing blood with a lot lower pressure to the lungs. Also, when blood goes with low pressure into the lungs, it's capable of maximizing the amount of oxygen that's diffusing. You're giving it plenty of time, right? When things go slowly, you absorb things very efficiently and you release things efficiently. If you're going way too fast, you're not going to be able to do any diffusion. Okay, so keep all that in mind. Again, an important point, think about why the right side of the heart generates such low pressure. Anyway, what is shown here is the left side of the heart because it generates high pressure and it's easily measurable. So you're dealing with left ventricular pressure here, right? And if you look at the cardiac cycle, the word diastole, look at the way you say diastole, right? I want you to physically imagine the chamber filling, right? So diastole is heart chambers filling, relaxing and filling, because when the heart chambers relax, they are decreasing their pressure. And whenever pressure decreases, fluid goes towards that area, right? Fluid always flows from high pressure to low pressure areas. And you can easily see that, right? If you open a gas tank, gas is going to fizz out of there because there's much higher pressure inside the tank and much lower outside. And liquids follow the same rule. And if you open the tap of a little tank, water's going to flow, right, automatically because, again, high pressure to low pressure gradient. And systole is when the chamber is contracting, okay? So when you're looking at the P wave, okay, what is happening is you will notice that the pressure in the ventricle, again, notice the left ventricle is what this is displayed in blue, right? So if you look at the pressure, there's a slight increase in pressure because when the P wave is happening, right, the ventricle has already gone through the T wave, right? It's fully relaxed and it's causing a suction force. This is called the thoracic pump, right? The heart is sucking blood in, okay, from the superior and the inferior vena cava. So blood is going through to the atrium and blood is collecting in the atrium. But at the same time, understand that there's some blood that is going down into the ventricles as well. So the change in atrial pressure is reflected as change in ventricular pressure. These two mirror each other, right? So pretty much at this point, so during the P wave, the mitral valve or the bicuspid valve is open. So whatever pressure changes, the atrium sees, right? The ventricle also sees. So those two are mirrored. And then when the mitral valve closes is right after the QRS, right? Makes sense because QRS signals for ventricular contraction. So ventricular cardiac muscle starts contracting, and this will immediately cause the chamber to start increasing its pressure. Look at the pressure increase here, right? And what is interesting is blood will pool in the ventricle and it will start increasing its pressure, okay? But the volume doesn't change because the aortic valve is closed until you hit this pressure where the pressure of the ventricle exceeds the pressure of the aorta. See, all these points, the pressure of the ventricle is less than the pressure of the aorta. So until you get greater than the pressure of the aorta, the valve cannot open, right? So when you hit that threshold point, the valve in the aorta opens towards the aorta. So blood starts getting ejected into the aorta. And now that that valve is open, you again have that mirroring. Remember, I told you, anytime mirroring happens, the valves are open. So here's an example where valves are open. Here's an example where the aortic valve is open. And so the pressure in the aorta, in blue, is the same as the pressure in the ventricle, right? Which means blood is flowing from the ventricle into the aorta. And then when the pressure drops, right, at one point, the aortic valve is going to close. Remember, all these valves only open in one direction, right? So when that closes, what you see immediately in the aorta is this very important physiological point called the dicrotic notch. So what is happening is you need to understand that the aorta is a very highly elastic vessel. And when the aorta starts pooling, so this is the important property of all elastic structures, including cardiac muscle. We're going to be looking at that when we look at cardiac output regulation. So whenever the any elastic vessel starts expanding, it's going to snap back like a rubber band. The more you stretch it, the stronger the snap back is going to be. It's called the recoiling force. And this is called Hooke's law in physics, H-O-O-K-E, Hooke's law in physics. So the restoring force is proportional to how much you expand. So the more you expand, the greater the recoiling force is going to be. And so the aorta will do that. And when the aorta does that, the pressure is going to increase tremendously, right, in the aorta. And this represents what's called a dicrotic notch. So what the aorta is really doing is adding pressure to the blood. So when aorta adds pressure to the blood, that's good because remember, you need blood to reach far corners of the body, correct? So, so the aorta is basically a pressure adding mechanism. It adds more pressure to the blood. This is why blood pressure is greatest in the aorta, right? And also, if you look at the blood pressure in the aorta, it waxes and wanes, right? Just like the pressure in the heart, because again, it is elastic. The elasticity of the aorta is really, really important. So when people get atherosclerosis, athero means aorta or artery, sclera means rock, right? It becomes hard as rock. It's lost its elasticity, right? Aorta loses its elasticity with age. and aorta loses its elasticity when people have lipid imbalance, right? So cholesterol gets deposited and it hardens the aorta, and aorta loses its elasticity, and that's not at all a good thing. That can lead to all kinds of cardiovascular problems, right? And again, here, notice that the pressure of the ventricle falls below the pressure of the aorta, so the valve is going to close. The mitral valve, I'm sorry, the semilunar valve is going to close. And notice that this relaxation, this drop in pressure, happens at constant volume. This is isovolumetric, but pressure is falling, so it's called a relaxation. Okay, so this phase is relaxation, right? And when the pressure of the ventricle becomes less than the pressure of the atrium, the bicuspid or the mitral valve is going to open, and you're starting all over again, right? So the cardiac cycle begins all over again. And you have two important sounds. S1 is the closing of the mitral valve, and S2 is the closing of the aortic valve, right? And so this is how the heart sounds correlate with the cardiac cycle. And again, I've given you another diagram which explains pretty much the same thing, right? One important change I want to highlight here is what is going on here with this little atrial bump, right? I told you that the bicuspid valve is closed here. So how come pressure is increasing in the atrium? I told you that the atrium is very thin-walled, correct? So when the valve is closed and the ventricle is filling up with blood, right, and blood is sloshing around in there, it's going to push on the valve. The valve's not going to open, but it's going to push, and that pressure is reflected in the atrium, and that's why you see this little bump. It doesn't have any physiological significance, but you're seeing that bump because the pressure in the ventricle is it's blood hitting the mitral valve, right? So when that's hitting the mitral valve, you're seeing that pressure becomes distributed, okay, into the atrium, and that's why you see this increased atrial pressure, right? And again, when the valve opens, notice that the pressures are mirrored. Here the valve is open, the pressures are mirrored. Here the valve is open, the pressures are mirrored. So notice that pattern, right? So the cardiac cycle is very, very important, okay? So these are some of the words, right, that we're using, right? One cardiac cycle is one cycle of contraction or systole and relaxation or diastole, right? So important are electrical events, which is the EKG, pressure changes, right, heart sounds, volume changes, and mechanical events, what's physically happening, contraction, relaxation, that type of thing. And that's what's shown here. So here's sound 1 and here's sound 2, right? So these are the various places where you can hear these sounds, right, for auscultation. So you're going to be doing this in the lab. And here's another version of the cardiac cycle as to physically what's going on. So imagine this as a cartoon and go through this. It should be very helpful in imagining what's going on, what's contracting, what's pushing blood where. And here's the whole thing kind of put together. The EKG, the pressure changes, the volume changes, right? So this is important. I want to go over this. So if you look at the volume changes, really what's going on is in the ventricle, right? So again, there's a small increase, right, in volume. And then, of course, blood is being ejected into the aorta, so there's a big drop in volume, right? Most of the blood is being pushed into the aorta, and then it starts collecting blood all over again, right? So, and notice they're all kind of correlated, right? And there are two really important points here. So this point is called the end diastolic volume, and this point is called the end systolic volume, and these two are crucial. So end diastolic volume is the maximum amount of blood collected in the heart, right, due to suction of the heart from the veins, right, superior and inferior vena cava. And end systolic volume is basically how much blood remains after the ventricle has beat, right? So the difference between the end diastolic and end systolic volume is called the stroke volume. How much blood is stroked into the aorta, right? So that's called the stroke volume. And a healthy heart will have maximum end diastolic volume, minimum end systolic volume, and will have maximum stroke volume. So maximum amount of blood per beat, which is exactly what we want. Now, understand that in atherosclerosis, when the aorta becomes rigid and not really ready to receive a lot of blood, you will end up with a very high end systolic volume. Blood remains back in the heart, and that's not a good thing because all the other organs are not going to receive oxygenated blood, right? You're going to compromise other organs. And not only that, the heart itself will not receive a lot of circulation because the local circulation in the heart is maximized during diastole. So when the heart is receiving blood into remember, we're talking about the left ventricle, right? So from the pulmonary veins, you're receiving oxygenated blood. When that's coming in, understand that as the atrium is receiving blood from pulmonary veins, the first dibs is for the heart. The heart takes the first dibs of that blood. Only then the rest of the body gets circulated with good blood, right? So if diastole is compromised, right, the first organ that's going to be affected is the heart itself. Okay, so please keep that in mind. And I will see you in the cardiac output lecture.